Hello world, it's Rational Pi, and I'm back here today to talk about the Millennium Prize problems. And we're going to be first talking about the P versus NP problem. That's the one I'm by far the most interested in, even though we're going to go through all of them. And this, as a recap, P equals NP is one of those computer science problems that it tries to take a very hard problem and a solution. And then if you're able to verify the solution quickly, but the problem itself is so hard to figure out, that's what's called an NP problem, or non-deterministic polynomial time problem. Polynomial time problems are problems that you can find, let's say you have 1,000 inputs, if you can find it within 1,000 steps or 1,000 iterations, or you find it in n squared iterations or n cubed, that's a polynomial. And the NP problems are those that are solved in, let's say, 2 to the n. For example, prime factorization. If you take a number and you want to try to figure out if it only has primes as its factors, then not only do you have to find out the factorization itself of that number, but then you have to test every single number you find to find out if it's prime. So there's at least 2 tests for every single number that you want to go through. And if you want to find the prime factorization of a very large number, the time it would take to figure out that factorization would just be so monumental that it just wouldn't be worth it. I mean, why would you want to spend years upon years to try to figure out this answer? But one of the most popular problems in the P versus NP universe is that of the traveling salesman problem. And the problem states that if you're a traveling salesman and let's say you start in Oklahoma City, and we have our MBA map here that we used in our A-star algorithm code. If you started in Oklahoma City and you needed to visit every other city in our network, what's the fastest way to visit all 30 cities? On the surface, that doesn't sound like that hard of a problem. And that's why initially some people thought it was just NP hard. And what NP hard is that the solution is easy to verify, but the problem itself is difficult. However, if you think about it, it's actually NP complete, which means not only is the problem itself hard, but then the solution itself is hard to back that up. And let me explain why. It's easy, so we found our easiest path from 1 to 17, okay? That one was pretty easy. We figured that out just using heuristics, and we've used it, the longitude and latitude stats. Right? But the problem is that, yes, we can just go through and brute force everything and figure out which one's the correct answer. We can figure out how to visit all 30 cities in the fastest way possible by using just brute force. Now, it would take forever, but we could find it. We could verify it. And we could compare it to everything else. But at the same time, finding the shortest path is the key here. That's what's hard to figure out. That's what's going to make it difficult, because if you start at 1, do you group all the other ones right next to it, or do you start going eastward? That's the key to it, is that, yes, we can figure out if one group of set numbers and set paths equals a full set, and then compare it to another one, yes, that one's less, so that one's obviously the right one. But that's not the key. The key here is to find the shortest path, and that's what takes the most amount of time. So the traveling salesman itself is an NP complete problem. And that's kind of what we're going to tackle here today. And I'm going to try to show why it's such a hard problem. If you remember in my MBA series, each city has at least 5 different nodes that's connected to, except for Utah, and east and west of Utah, because Utah's that connecting point between the two. And if you really wanted to take a look at it, you can approximate the amount of iterations to be 30 factorial, which, let me bust out my calculator, I don't imagine it would be a very small number. So let's see if my calculator even has factorial. It sure does. 2.652528 times 10 to the 32, right there. I don't know if you can see that, but there you go. So that's how many iterations it would take just to find the approximate shortest path to visit all 30 cities in my neural network here. And it just doesn't make any sense. So that's why this P equals NP is such a huge deal. It's because if we can figure out a way, without using approximations or heuristics, a true way to figure out the shortest path to visit all 30 cities in a polynomial time standard, then if you can prove it, that solves P versus NP. Because if you solve one problem and prove that P is equal to NP for that problem, you have then proved that P equals NP for all problems. Alternatively, if you find out that P does not equal NP for one problem, you've solved that P does not equal NP for all problems. And either solution would satisfy the Millennium Prize problem qualifications. There's also a third train of thought, and that is just that there's no way to prove that P is ever equal to NP, nor is it able to prove that P is not equal to NP, and it's called the uncertainty principle. There's a book by Gödel, Escher, Bach, I can't remember the name of it off the top of my head, but it's a very fascinating piece into this sort of problem. Minesweeper, coincidentally enough, I just made that Minesweeper video, is another problem that P equals NP can be utilized in. And I quoted the article in my last video regarding this series. So that is kind of where we're heading towards. Next video, we're going to actually throw some numbers at you. I'm going to try to pick one conference or one division and then actually try to see how long it takes to actually calculate the amount of time it would take just for 5 cities to figure out what would be the shortest path there. And then we may expand it and expand it, and see when it becomes just too unruly. So I hope that makes sense. That's the premise of P equals NP. In the next video, we'll be going over some numbers. The video after that, we're going to be talking about some research that's being done within the problem. And then the last video after that, we will kind of summarize all the research that's going into P versus NP, and then we'll move on to the next problem. Do you have a problem that you want to focus on next? Let me know in the comments below. If you have any clarifications or any questions, I'll answer them to the best of my abilities. Again, I'm by far no computer science expert or anything like that. I'm just a guy who's really fascinated with this kind of stuff. I would like to give a shout out to the OKC Sharp program for putting on a very nice presentation today. There's some guys that presented on some topics in C# here in Oklahoma City, and that will end our video today. So I will see you guys in the next video. Have a good day.